Something that almost always comes up in an implicitly defined fashion is the concept of a fat circle. Now, we know from our experience that a circle, from a mathematical perspective, looks like x squared plus y squared is equal to r squared. Specifically, this would be a circle that's centered at the origin. For a fat circle, this is what you get when you have x raised to an even power plus y raised to an even power is equal to r raised to that same even power. So this is where n will be greater than or equal to 2, and n is an integer. I would encourage you to check out some graphs of these. Fat circles look like what would take place if a circle and a square love each other very much and they want to have a baby. Well, it winds up looking like a fat circle. So for an example of a fat circle, I would like to do x raised to the 4th power plus y raised to the 4th power is equal to, let's do 2 raised to the 4th power. So 2 raised to the 4th power will be 16. What I'm interested in doing for this example is implicitly differentiating this, but I'd like to do it twice. I would like to find dy over dx, but I'd also like to find d squared y over dx squared. That'd be the second derivative of y with respect to x. As we did for our other implicit differentiation examples, I'd like to start by taking a derivative right away. We're operating under the assumption that y is a function of x, so when I apply these derivatives, the first derivative will simply be the power rule. Y to the 4th will be a combination of the power rule and the chain rule. Over on the right hand side, we'll have one of the easiest derivatives we're going to see in this particular video. Derivative of 16 would simply be 0. Next, we're going to perform a little bit of algebra to isolate the dy dx on the left hand side. We can do that by saying, let's first subtract 4x cubed from both sides, throw a minus on there, and then divide both sides by the coefficient of dy over dx. So divide by 4y cubed and divide by 4y cubed. This is going to allow us to arrive at the fact that dy over dx is going to be equal to negative. We can reduce the 4's and be left with x cubed divided by y cubed. Once we're in this form, we are going to go ahead and differentiate one more time, and we're going to do so implicitly. So differentiate the left-hand side and differentiate the right-hand side. Now, as far as the left-hand side is concerned, that is simply going to be the second derivative of y with respect to x. So d squared y over dx squared. As far as the rest of this is concerned, we'll start with the fact that the negative would be a constant multiple. So I'm going to factor that out immediately. And for x cubed divided by y cubed, I'm going to treat this as a quotient. So I will be applying the quotient rule. Quotient rule says that this will be low, d high, derivative of the top, less high, d low, derivative of the bottom, over the square of what's below. Now this definitely doesn't finish the derivatives for us, but it does give us something that perhaps we can work with. So y cubed, that'll stay y cubed. Then we have the derivative of x cubed, that'll be 3x squared, minus x cubed times the derivative of y cubed with respect to x. That'll be a combination of the power rule, 3y squared, and the chain rule, dy over dx. If I square this y cubed, I will get y to the 6th power. That's like saying y times y times y times y times y times y. So a total of 6 y's there. The next thing I'm going to do is make a substitution, because I happen to know what dy over dx is equal to. In fact, I have it right here. So I'm going to make this substitution, negative x cubed over y cubed, into this expression right here. I'm also going to clean this up a little bit. We'll call this 3x squared y cubed minus 3x cubed y squared, that's these three factors here, and then the dy over dx will substitute as negative x cubed over y cubed. This is all still over y raised to the 6th power. Now obviously there's still a little bit more cleaning up to do here, so let's clean. Keep that negative sign out front. This doesn't really require a whole lot of cleaning up, so we'll leave it as is. Now for this portion, we have a negative times a negative, that'll be plus. We have x cubed times x cubed, coefficient of 3 first, then x cubed times x cubed, then we have y squared divided by y cubed. If we subtract the exponents, that'll leave us with y to the negative 1st power. However, y to the negative 1st power is like saying, let's put a fraction inside of our fraction, which, according to my French teacher, is no bueno. So what I'm going to do is multiply top and bottom by y. This y will effectively cancel out the extra factor of y we would have in a denominator. Now with that in mind, we're running a little low on space here, so we are going to jump over to a new page. Yeah, just like that. Good stuff. So with that in mind, that y is going to distribute to both terms in the numerator. Part of it will cancel with the second term, but on the first term, it'll simply increase the power of y by 1. And we'll get x squared y to the 4th plus, for the second term, I guess technically it is just increasing the power of y by 1 to get to y to the 0 power. In the denominator, we are going to have y to the 7th power. Now if, as my student, you arrived at that statement, I would say good for you. Here's full credit for the problem. Excellent job. However, there is one additional thing that you can do, which is observe that there is a greatest common factor in the numerator. If we factor out that greatest common factor of 3x squared, then we would be left with y to the 4th plus x to the 4th. Now, as a reminder of where this whole party got started, we had started this process by saying that x to the 4th plus y to the 4th is equal to 16, which means that this portion right here, technically, in this problem, would be equal to 16. If you miss that substitution, I'm going to forgive you, but, you know, not everybody will. So we'll substitute in a 16 for that value, and then continue to simplify the numerator. Our final answer for the second derivative of y with respect to x will be 48x squared all over y raised to the 7th power. So that is how you find second derivatives implicitly for fat circles.